Okay. Hello, people. Very good evening. I thought I was waiting for students to join, but I think that's it, I guess. Right. So, can I know which topic is going on? Guys, which chapter is going on or which topic is going on? Nobody knows what chapter is going on.
Thermodynamics.
Thermodynamics.
Okay, thermodynamics is going on. Fine. So, did you study about enthalpies? First law of thermodynamics? Thermodynamics, how many classes got over? Nice. Thermodynamics, how many classes got over? Okay, what was the last thing you studied in thermodynamics? If you have taken notes, can you just go through that and tell me what was the last thing you studied?
Sir, can you teach it from the start itself?
Sorry?
Teach it from the starting of the chapter itself.
Yes, sir.
Okay, starting itself. Cool. We can do that. Right. Fine. All right. Let me share my screen and we'll start. Excuse me. Okay. Right. So thermodynamics it is. So in physics also you have this chapter, right? And in chemistry also you have this chapter. So 60% of the chapters more or less will be same in both chemistry and physics, but certain things will study here and certain things will study there, and those things will not study here and vice versa, right? Okay, so basically we'll be studying chemical thermodynamics is what is required for chemistry. That part of thermodynamics only we'll study. Anyways, okay. So what do you mean by this term thermodynamics, right? Thermo, we know, means heat, something related to heat. And dynamics, this word talks about movement, right? So we are going to talk about heat movement. That's it, right? That simple phenomena, heat movement, is actually going to be caused by so many things. Even with the microscopic level, with the atomic levels, you'll be able to understand how this heat movement or heat transfer happens, right? Now, when we say heat movement or heat transfer, right? So first you have to understand from where to where the heat transfer is happening, right? That you have to understand, right? So for you to decide from where to where, first of all, you need to have a boundary, right? From that to this, you should have some kind of segregation among something. From that, you say this place to this place it is flowing. You need to have some kind of boundary, right? First of all, we need to define this boundary, right? For example, say whatever room you're sitting, inside that room, I want to see what kind of heat changes or heat transfer is happening. So the walls of the room becomes my boundary, right? Okay. Say for example, if I want to speak about my own body, right? What kind of heat transfer occurs across my body? My entire body is my, entire body's, perimeter. Whatever is the perimeter of my body becomes my, what boundary, right? And we're going to study about, say, once you define the boundary, what is going to be inside the boundary, right? What they say, if this is inside and if this is outside the boundary, right? Whatever is inside the boundary, we will call that particular place as system. S bar M is a short form for system, right? And whatever is outside the boundary, right? That we call it as surroundings. Right? Say, for example, it's all about how you choose the boundary. For example, I want to speak about what are the heat changes happening across my heart, and only my heart and not the entire body, right? So but the perimeter of my heart becomes, my system, right? And whatever is outside the perimeter, include my hands and lungs and other table which is there and other neighbors, everybody becomes my surroundings, right? So I hope you understand. Depending on how you define the boundary, based on that, the system and surroundings will be differing, right? It's all about how you define the boundary first. Okay. So heat changes can happen from this side to this side, that is from system to surroundings it can happen, or from surroundings to system, heat can transfer, right? So this small thing that you see that the heat transfer occurring between a system and surroundings, we are going to have a hell of a lot of investigation to do in this chapter. The entire chapter is all about this, right? Okay, fine. Now we have understood, three terms here. One is your system, whatever is the area of interest, right? And boundary is the one which separates the system and surroundings, and surroundings is whatever is outside the boundary is your surroundings. That we understood, right? Now, the different types of systems we can have. These systems which we see, right, broadly we'll be able to classify them into four types, right? First one is what is called as your open system, right? And next one is what is called as a closed system, and we have something called as isolated system, and we have something called as adiabatic systems. Okay, right. So now what do we mean by all of these things? It's all about how the heat transfer or the mass transfer is going to happen. It's not only about heat transfer, right? It's also about sometimes mass transfer. Some amount of substance is getting transferred between the system and surroundings, right? Okay. So the perfect example we can have for an open system is, say I have a vessel in which I have some water and I'm heating it. Right now, what is going to happen? Since now initially this would be at 25 degrees Celsius, right? Now, if I start heating, it is going to go, temperature is going to rise to say 100 degrees Celsius or whatever it is, right? The temperature keeps on increasing. The heat flow is happening from surrounding the system. The system is this. The system is my water, the beaker containing water. The beaker is my boundary, right? So how the heat flow is happening from the surroundings to system, it is flowing the heat, right? This is the heat direction of heat flow. Okay. Right. Now, because of heating, what is going to happen? This water in liquid state is going to go into vapor state, right? So we'll understand that H2O gas is going to come out of this, right? So what happens now? This is a boundary, right? Now, outside the boundary, what are you seeing? There is going to be some amount of mass getting transferred also. Say, if I start with 10 grams of water, now after some 2 minutes, you will see only 8 grams of water, or say 6 grams of water, because some amount of water would have gotten evaporated or say boiled, right? Okay. So what you understand from open system, you can have both mass transfer. Yes, we see that the amount of water between the system and surroundings are changing, right? And also you can have heat transfer between your system and surroundings can happen. Okay, right. Now, what can be closed systems now? Now the same thing I'll do. Okay, I will take water, but this time in a closed vessel and I'll heat it. Now what will happen? Obviously, the heat is flowing from system, surrounding system, that is happening, yes, right? But even though the water will convert to water vapor, whatever is the amount of H2O which was initially there, that nothing can escape. Say if at all I start with 10 grams, it will stay as 10 grams only throughout the process, right? So what you understand in case of closed system, heat transfer can happen, right? But mass transfer won't happen, right? The amount of substance, remains unchanged throughout the process, right? Okay. Now, last one, next one is what is called as your isolated system, right? So isolated system is where, say, we have a tumbler of water, right? And we are just doing nothing to it. We are just keeping it, right? So what are you seeing here? You are seeing that the heat transfer also will not happen and mass transfer also will not happen, because we are not doing exact heating process as such, right? Nothing we are doing to it. Okay. And the last one, the adiabatic systems, right? Now, the adiabatic system is the perfect example. Right. Say, for example, adiabatic systems, we will take a container, right, in which we'll put NaOH plus HCl. Okay. And then we will insulate it. Okay. This is insulation. Right. Now, we know this NaOH plus HCl is what kind of reaction it is? It is endothermic or exothermic? NaOH plus HCl is endothermic or exothermic? What is endothermic? What is exothermic? You don't know. What is endothermic and what is exothermic?
Endothermic is where you absorb energy is absorbed, and exothermic is where it is released.
Energy is released. That's good, right? So in this reaction, NaOH plus HCl, energy is going to get released or energy is going to get absorbed. You studied from your 10th class, right? All neutralization reactions are dash in nature. This is neutralization. Yes, they are exothermic, right? The moment you react NaOH and HCl, this is a neutralization reaction. What is a neutralization reaction? Acid plus base reaction is what is called as neutralization reaction, right? So you'll understand that the heat will be released during these reactions. Okay, so this container, right, will try to give out some heat, right? It will try to give out some heat, right? But since it is insulated, the vessels, this thing is insulated, the heat flow will not happen from your system to surroundings. Even though it is exothermic, you see that because this thing is insulated, you understand that this is not coming out during this process, right? But anyways, if you put a thermometer inside, this is the thermometer, and if you put it inside, now you will see that initially, before only NaOH or HCl is there, some temperature would have been there, right? Now after you add the other one, you will see that the temperature keeps on rising. Why? Because it is an exothermic chemical reaction. Inside, whatever Q is there, that is going to make the system very hot, and in that process, the temperature rises, and you will see that the reading in the thermometer keeps on increasing. Right now, what are you seeing here? You are seeing that whatever is the amount, whatever we have kept, so the amount of NaCl, amount of NaOH, HCl, everything, whatever is there will not change, right? I mean, mass can change, but in this case, even if you see that, say there's a small this thing to which the H2O gas can come out, something like that. So what you understand is heat transfer is not happening here. That's all you have to understand, right? So in case of adiabatic systems, heat transfer should not happen and mass transfer should happen, or say mass transfer can happen. That's how it is. Okay, but heat transfer strictly it should not happen. No heat transfer between your system and surroundings. Okay, right. So that is about whether heat transfer or mass transfer is happening across a particular system, particular boundary or not between system and surroundings. Right. Now, next thing what we want to learn in order to understand how this heat transfer happens is how do you describe a system? Description of a system, right? Now, how do you describe? For example, say if you want to define me, say I don't know, you're not seeing me, right? So say that sir is very tall, he's having a beard, I don't know, he's stupid, whatnot, right? Say like that, you will have some description about me, right? So like that, we'll have some description for a system also, right? Now, the thing which is used for describing a person, for example, is height or color, or I don't know how he looks, whatever, right? Those parameters you have, right, for describing a human being, like that, that particular parameters which you'll be able to describe a system, right, are what are called as your, properties of the system, right? Properties of a system. Okay. They're also called as variables of the system, right? Fine. Anyways, right now, based on if you study these things, like if you using these things, we'll be able to talk about a system. Now, here in most of the cases, we will be talking only about say piston, right? I mean a vessel with a piston. This kind of systems only in most of the cases, in at least for our syllabus, we'll be talking about, right? Now, what and all do you think I have to use for describing it? For example, say, if you think about it logically as a science student, you need to know what is the pressure, right? You need to know what is the volume. You need to know what is the temperature. And if at all gas is inside, how much amount of the gas, the number of moles of the gas, right? So these and all are the things you will talk. Okay, this much amount of gas is exerting this much pressure, and because of that, the volume is this much, and this is all happening at 25 degrees Celsius. That is how you describe the system, right? Okay. Anyways. So these properties or variables which are using for describing the system can be of two types, right? Now, again, that is going to make a lot of sense. Why are we dividing into two, right? One are what are called as your intensive properties or intensive variables. And the next one is what is called as your extensive properties or extensive variables for that matter. Okay, right. Now, what do you mean by this intensive and extensive properties, right? For example, say I have in a vessel in the same room, okay, we are in the same room. I have say 10 grams of water here at 25 degrees Celsius. Here, say I put 25 grams of water, right? What will be the temperature here? What will be the temperature? We are in the same room, right? Say if I take 1 tumbler of water or 2 tumblers of water, temperature will be what? Guys, what will be the temperature? Are you able to understand the question? I have 10 grams of water, or say I made 2 tumblers of water, or I made it into 2, right? What will happen to the temperature? First of all, guys, everybody will go to the chat, right? Now you will type in the chat box saying whether temperature will change or temperature won't change. Change or not. Change or not is what I go to the chat box and type the answers.
Sir, I think it will not change.
Okay. Any other answers? Won't change. Okay. Anybody else? Okay, fine. That makes sense, right? Like, I don't know, like if you're going to do it in your own homes, wherever you're sitting, take 1 tumbler of water, drink it, and say take 2 tumblers of water and mix it and drink it. Are you going to have any difference in the amount of temperature, or it is going to, just because you're adding, on another tumbler of water, it is going to become more cold? Does not make sense, people. You're taking it from the same room. Everything is same. Surrounding this thing is same, right? So it doesn't matter. Here also, I'm going to have 25 degrees Celsius only, right? Now say another example I'll take. Okay, say I have some water, right? Say I have some 10 ml of water. In this, I have put 1 gram of sugar. Okay, now what I'm doing is, from this, I am taking 1 teaspoon, right? And putting it here, right? And I'm taking 2 teaspoons of this and putting it in another this thing, right? Now tell me, in this beaker and this beaker, what will be the densities? The densities of these two will be same or different? If I put 1 teaspoon, if I take 1 teaspoon and check the density, and if I take 2 teaspoons and check the density, will the density be different or same?
Same, sir.
Definitely, right? We have already completely mixed it thoroughly here, right? And we're taking 1 teaspoon and it's completely mixed, right? So definitely that density is still going to be, same, right? Here, for example, the density here is 1 divided by 10, basically mass divided by volume is what is density, right? Here also it would have been 1 by 10 only. Here also it would have been 1 by 10 only, right? Because the same solution only you're taking, right? Twice or thrice, doesn't matter. Right? So what are you understanding between your temperature and density? What is the conclusion? What is the conclusion from the from temperature and your density? What is the conclusion? Tell me, guys, what is the conclusion? Nothing you can conclude by doing these two. Say, okay, fine. But say I have 20 ml of water here. Okay. Now what I'm doing is I'm taking 1 teaspoon, I'm putting it here, and I'm taking 2 teaspoons and I'm putting it here. What about the volumes here and here? It will be same or different? What about the volumes? I have 20 ml of water, 1 teaspoon I'm putting in 1 beaker, 2 teaspoons I'm putting in another beaker. In both the beakers, will I have volumes to be same or different?
Different, sir.
Volume is different. What is volume? The amount of liquid right here. If I put 1 teaspoon, for example, say if I had only 1 ml, here I would have had 2 ml of this thing, right? Okay. Now what is the conclusion? Now at least can you tell me here on the previous 2 examples regarding your density and temperature, what is happening?
Sir, they are independent of the amount they are taking.
Exactly. Right? How much amount of substance I'm taking is not mattering for these kind of properties like temperature, density, and all. But say if I take mass, volume, or number of moles, for example, these stuffs, right? Those stuffs are actually depending upon how much amount of substance I'm taking. right? So that is that based on this only we have this classification: intensive properties and extensive properties. Intensive properties are independent of the amount, whereas your extensive properties are dependent on the amount of substance, right? So what can be examples of intensive properties? Say temperature, density, I don't know what else I can think of. These two are the only more major things are there, right? And in case of extensive properties, you have any types of energy, any form of energy. That can be heat energy, light energy, blah, blah, blah. Any types of energy will be this thing, right? And then even your entropy, like I already write one term here, but we'll see about this later. Entropy is also an intensive property. Okay. Anyways, so the energy, any form of energy, number of moles, volume, mass, anything, any of these things are going to become, extensive properties are going to depend upon the amount, right? Fine. So using these intensive properties and extensive properties, you will describe how a system is going to be, or how is it going to behave if I do something. For example, say there is a way to describe a person like this also, right? If at all you lie to him, he is gonna, he's going to become very angry. That way, right? Say like that. If at all you increase the temperature of system, this much volume will increase, or say number of moles will change. Like that also you'll be able to describe the system. So it is not only about describing the system in that particular state. Now, when I say state, in those particular conditions, when I change the conditions, say for example, I increase the temperature or decrease the temperature, how the system is going to behave also will be able to predict once you know this particular property of the system. Is it not? Right? Now, for you to know anything and everything about the system, if I do this, this will happen. If I do that, that will happen. Everything you will be able to predict. And thermodynamics is a very powerful tool, right? It requires only very, very small informations, or say very less number of informations for you to predict so many things, right? Now, for 100% description, in the sense that you want to know anything and everything about the system, what the system is, how it will behave if I do this, if I increase the temperature to 25 degrees Celsius, which will happen. If I compress by increasing the pressure this much, this will happen, right? Everything and anything you want to know about a system, right? So for 100% description, thermodynamics require only 3 things. Okay, what it requires is that I require 2 intensive properties. Okay. Any 2 intensive property I need. There are so many intensive properties, don't worry about it. Any 2 intensive properties I need, right? And one more thing, what I need is the number of moles of the substance present inside the system. Okay, right. But you can ask me, sir, for example, say if volume is given to us, how do we work with it? Right? Because volume is not an intensive property, it's an extensive property, right? So thermodynamics has an answer for that also, right? So what it says is that there is a way to convert an extensive property into an intensive property. Okay. Now, how do we do that? That's very simple. If I write any extensive property EP, I divide by the number of moles, it is going to become an intensive property. For example, if I have energy in joules, if I divide by the number of moles, it is going to become energy, but here the unit is going to be kilojoule per mole. Right, n becomes the number of moles, right? So whenever we do this per mole, wherever you see this particular term coming, any quantity per mole, any quantity per gram, any quantity per ml, something like that, right? Whenever you are saying that per ml this much, per mole this much, that means a specific amount there. That amount will not change, right? So if the amount won't change, obviously this particular property also won't change, right? Say for example, if you take volume is an extensive property. If you divide by the number of moles, we represent it by Vm. Vm is what is called as molar volume. Molar volume is nothing but volume of 1 mole of the gas. Is it not? Right? Then I can say if 1 mole of gas is this much, then 2 moles of gas is going to be how much? That I'll be able to predict. But this Vm will not change. Per mole, what is the volume? That won't change irrespective of how much amount of gas you have. It doesn't matter if I'm going to have 5 moles. But all I want is for 1 mole, what is the answer? Right? So this is the way that you'll be able to convert your extensive property into an intensive property. Okay, fine. Right? Next. Fine. Now, next thing is, right? There is another, so fine. We're talking about heat. Let us continue it like this, right? Now we'll connect this heat, even your, and I said energy is also going to be an extensive property. Anyways, right? So whenever we do this so-called heat transfer, right, there is very lot of consequences, right? Now, the first consequence, what we'll understand is that there will definitely be some change in temperature. Okay, right? Fine. So we need to get some kind of relationship between your heat and temperature. Is it not? Right? So all we can understand is, say, if I have two bodies, right? Now, I don't know, this is having, say, 10 joules of heat energy, and this is having 20 joules of heat energy. Okay, right? Now I'm keeping them in contact. Okay, now I'm keeping them in contact, right? So what is going to happen, do you think? Obviously this is having a larger heat content, this is having a smaller heat content. The heat is going to flow from this body to this body, is it not? And that heat symbol will always represent with Q. Q represents heat, remember that. Okay, right? So when I keep them in contact, heat is going to flow from the hotter body to the colder body, right? So initially, I don't know if this was at some 35 degrees Celsius and this was at some 25 degrees Celsius. I don't know, some just giving some random values before we are keeping in contact, right? Now, what is going to happen? Now you see that this temperature will keep on decreasing and this temperature will keep on increasing. And this heat transfer, so-called heat transfer from the hotter body to the colder body, is going to stop at a point of time, right? At what time there will not be any heat flow? Guys, at what time there will not be any heat flow? Or what is the conditions they say that this heat flow after some time will become zero, right? What is the condition?
Sir, when temperature of will be same.
Temperature what?
Temperature of the bodies will be same. That time it
Exactly. When
stop.
you see that the temperature of both the substances becomes, I don't know, some say 28 degrees Celsius. I'm just saying here on the atom value. It might be different depending on the bodies. Okay. Say if it is 27 degrees Celsius, 28 degrees Celsius, both of them, now there the heat content also will be remaining similar. So you'll see that the heat flow will not happen. Right. Now at this point, when you see that there is no heat flow, right? You will see, you use a term there. You will see that you will say that these bodies or these two systems are in thermodynamic equilibrium. You will say, right? You will say that these two bodies are in thermodynamic equilibrium. So what do you understand with thermodynamic equilibrium? No heat flow will happen between your two systems or between system and surroundings. If I say that system and surrounding are in thermodynamic equilibrium, then you'll say that between system and surroundings, there will not be any heat flow happening. Is that what you understand? Okay, right. Just give me 1 second. I'll be back. Just give me 1 second. Right. Okay. So we understood what do you mean by this thermodynamic equilibrium. Right. So that we understood, right? So now this is a good time to actually have you understand that. Say we'll take another case. Okay. Now say there is another case where I have this temperature was 25 degrees Celsius and this temperature was 50 degrees Celsius. And say again, the heat flow is going to happen from the hotter body to colder body. Say, let me call the amount of heat transferred here as Q2. And here we'll say that the amount of heat transferred is Q1. Okay. Now comparing Q1 and Q2, guys, which do you think will be greater? Comparing Q1 and Q2, right? First case, it is the same transfer is happening. But different amount of heat transfer would happen because, I don't know, you have to think, right? And if different amount of heat transfer is happening, which will be higher, Q1 or Q2? Go on. It might be a guess also. Go to your chat box and type Q1 or Q2, guys. Which one will be greater? Go on. Start typing. Which will be greater? Q1 first case, Q2. Q2 second case. Which do you think will be greater? Nobody wants to answer. Say if it is a guess game, what do you think? Q1 or Q2? Guys, are you there?
Sir, can you repeat the question again?
Okay, that you can ask, right? Okay, what I'm asking is, right. So we said, right, this time we had 35 degrees Celsius and 25 degrees Celsius. Here we are saying that some amount of heat is flowing from this body to this body. This heat is flowing. We say it as Q1. Now we are saying that we have a second case, right? This side, this time, this body is at 25 degrees Celsius and this body is at 50 degrees Celsius. Okay. Now from this side, here also we see that the heat flow is going to happen from the hotter body to the colder body. Yes. Say that amount of heat flow which happened is Q2. So Q2 will be greater or Q1 will be greater. What do you mean by Q1 and Q2? The amount of heat transferred in the first process, the amount of heat transferred in the second process, which will be greater?
Sir, I
Or
think
which
it will be equal eventually.
no. Like, okay, they will eventually become, say, I don't know, some temperature. That is okay, right? But to attain that same temperature, do you think same amount of heat flow also would have happened?
Sorry.
No, sir. I think it would have gone from the higher thing, which is hotter to the one which is colder.
No, that's what. Now here you understand that this body is hotter, 35 degrees Celsius. This body is colder. Some heat flow is happening, right? From hotter body to the colder body. That we understand. Here what we are seeing, this is at 25 degrees Celsius, this is at 50 degrees Celsius. Here also, this is the hotter body. This is your colder body and heat flow is happening, Q2. But the amount of heat I'm telling is different. Or, I mean, I don't know. That's the argument here. What do you think? And eventually they both will be reaching some same temperature. They say here it was 28 degrees Celsius. And I don't know, here it would have been some 33 degrees Celsius. I'm saying some approximate values. Okay. Now what do you think? Q1 will be greater, or say the heat transfer in the first process will be greater, or the heat amount of heat transfer in the second process will be greater?
Second process.
Okay, right. That I think that should be making a lot of sense to all of you, I guess. Now, why is it like this? Because the colder body's temperature in both the cases is 25 degrees Celsius only, right? But the hotter body is hotter here because it is already very hot, 50 degrees Celsius, and here it is less hotter, right? So obviously, from a very hot substance to a cold substance, more heat flow will happen than from a little, hotter substance to a colder substance. I hope that makes sense, a lot of sense, right? Say, if I have another case, if I give you, say, if I have something at, I don't know, some 3 degrees Celsius, and this is at 100 degrees Celsius, and say, this is at, I don't know, some 10 degrees Celsius, and this is at 100 degrees Celsius, and you see that this is this is Q2, and this is Q1. Which will be greater among these two? Q1 or Q2?
Sir, Q1.
Yeah, that makes sense, right? Again, now what are you seeing here? Here it is very hot. Here also it's very hot. 100 degrees Celsius, 100 degrees Celsius. Here it is at 3 degrees Celsius, very cold, right? And here it is quite warmer than 10 degrees Celsius I have, right? So definitely to 100 to 3, you will have a lot of heat exchange happening, whereas from 100 to 10, the amount of heat transfer will happen, but that would be less. Q1 will be greater. Say, let us take another case. I am going from I don't know, this is at 30 degrees Celsius, and this is at 70 degrees Celsius. And another, this is say Q1, say this side Q1 is moving, and say another case is at 20 degrees Celsius, and say another case we have this is 20 degrees Celsius, and say this side I have, I don't know, 50 will take, yeah, 50 degrees Celsius, and this is I telling is Q2. Now this time, which is greater, which is lesser? This time both the temperatures are different, right? Now how will you do? Now which reading will be greater? So guys, I don't know whether you understood the trick. The trick is that the Q, that is the amount of heat transferred, is directly proportional to the change in temperature between the two bodies. Is that what you not understand it, right? Say first case, let us take first case, the delta T who is greater, we decided, right? And if you go to this case, the temperature difference between this is 97 degrees Celsius, because 100 here it is 3 degrees Celsius, and here delta T is, I don't know, 90 degrees Celsius. Again, we said that this was greater because higher T, higher delta T. And what else? Where we took? Here. Now, with respect to using all these, again, we can say that here the delta T is 40 degrees Celsius. Here the delta T is only 30 degrees Celsius. The meeting chalega. Right. So here the delta T is 30 degrees Celsius. So again, we can say that Q1 will be the greater one because there is more change in temperature between the two bodies. Right. So this we can always say, right? Q is equal to Q is directly proportional to delta T. Right. The more and more is the difference in temperature, more and more heat flow would be there, is what you understand. Anybody has any problems with this? What we have learned now? Right? Okay. Now, obviously, to remove the proportionality sign, we'll make a constant, right? And that constant will be called as some C, del T. We'll write. Okay. Okay. Now, this C in this equation, obviously Q is the heat, right? This is your change in temperature, delta T, right? And your C is what is called as your heat capacity. Okay, right? Fine. Now, this heat capacity, I cannot just define it like that. Okay, this heat capacity, heat capacity is for any given statement. Okay, but if I divide this heat capacity by the mass, or say if I divide the heat capacity by the number of moles of the system, right? Now these two terms become something called as specific heat capacity. And I think you are able to understand what I am doing here, right? The amount of substance, how much has that also plays a role in these things. I don't want the amount of substance to play a role. So what will I do? I will can't divide that with number of moles or by mass to convert it into an intensive property. That is what that is all I'm trying to do here. Okay, so heat capacity is an extensive property, whereas your specific heat capacity is an intensive property. That's what you understand, right? Okay, and this C by M we write it as Cm, right? And this we write it as Cn sometimes. Okay, this Cm is what is called as your mass heat capacity. Mass heat capacity. Right? And this one, Cn, is what is called as your molar heat capacity. Right? The Cn is what is called as your molar heat capacity. Okay, if I divide by the number of moles, it's called molar heat capacity. If I divide by the mass, it's called mass heat capacity. And both are called as specific heat capacities together. Right? Okay. Now, how do we define this? This definition is going to be very, very important. Okay. Now, please take down, guys. I'm going to define the Cm, mass heat capacity is what I'm going to define. Please take down the definition. Take down. It is the amount of heat required. It is the amount of heat required to raise the temperature. It is the amount of heat required to raise the temperature of 1 gram of a substance. That's very important. 1 gram, right? It is the amount of heat required to raise the temperature. Okay, right? What did I say? Yeah, I was telling it is the heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius or by 1 Kelvin. Okay, I'll repeat the entire statement one more time, right? It is the heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius or by 1 Kelvin, right? So if you just read the statement one more time, you will actually understand how are we defining this heat capacity. If I go back to this equation, right? So if I see that this delta T, right? Say I start heating a substance, right? Obviously, when the temperature is raised by 1 degree Celsius, or say the change in temperature, it was 25 degrees Celsius, now it became 26 degrees Celsius, right? For that 1 degree temperature rise, how much heat energy you supplied? And if I put delta T is equal to 1, what happens? Q is equal to C. Isn't that? So it is the heat energy which is required to raise the temperature of the substance by 1 degree Celsius. But the amount of substance should be 1 gram, obviously. Where you take 1 gram of substance, you heat it to a certain extent where the temperature becomes raised by 1 degree Celsius. So in that process, amount of heat energy supplied is nothing but your heat capacity. Right? Okay. So same way can we define this one? Right? That is your molar heat capacity will define. Okay. Take one, people. Molar heat capacity. We are defining this term. Molar heat capacity. Right? The definition goes like this. It is the heat required. It is the heat required to raise the temperature of, it is the heat required to raise the temperature of 1 mole of a substance. Now 1 gram becomes 1 mole, right? To raise the temperature of 1 mole of a substance by 1 degree Celsius or 1 Kelvin. Right? Okay, so last time we took 1 gram and we heated till the temperature increase was 1 degrees. Now this time we are making sure that we're taking 1 mole of a substance. Now 1 mole, for example, 1 mole of oxygen means 18 grams. Right? So that I take and I heat it. How much heat energy is required for raising the temperature by 1 degree Celsius? Again, is going to be called as your molar heat capacity. Okay, right? Fine. Now we'll be able to write 2 equations now. So Q is equal to MC del T, and again we can write Q is equal to NC del T. Now you are using both C and D here, but here M represents mass. So here N represents moles. So here we are talking about molar heat capacity here, and here we are talking about mass heat capacity, depending on what data is given to you in the question. If at all they say about 1 gram, and if you see that what is the unit of this mass heat capacity, it is going to be joule per gram, because we are dividing it by joules per mass per gram. And in this case, you will see that the unit will be in terms of joule per mole. Okay. Right? I mean, joule per kilogram per degree Celsius. Right? That's what you will have here, because per degree Celsius, right? Again here per degree Celsius, or it can be joule per mole per Kelvin. Here it could be joule per gram per Kelvin. Would have been your units. For molar heat capacity, mole should come. For mass heat capacity, gram should come. Right? Okay, both are good equations. If at all mass is given and your mass heat capacity is given, you have to use this. If at all number of moles is given and molar heat capacity is given, you have to use this. Okay, right? Fine. So that is about this equation. So this molar heat capacity which we have, right? For chemistry, mostly you'll be using this only. Okay, molar heat capacity which we have, right? We will be actually finding it in actually two conditions, right? One at some conditions called as a constant pressure conditions, right? Or you can measure them at constant volume conditions. Okay. And if you measure that particular heat capacity, molar heat capacity at constant pressure at the process where the pressure is constant, that heat capacity, molar heat capacity represented as Cp, right? Cp is the molar heat capacity at constant pressure. That's how we define it. Same way, if I find the same thing at constant volume, I'll represent as Cv, C subscript V, and this I'll write it as molar heat capacity at constant volume. Okay. So we will be able to write one more equation for Q in terms of your molar heat capacity. Now you understand that the overall heat capacity is going to be equal to the sum of these two heat capacities, Cp plus Cv, right? So you can write overall Q will be equal to Ncp del T plus Ncv del T. This is a very important equation. Okay, Q is equal to Ncp del T plus Ncv del T. Okay, right? So I think we'll stop with this for today. Okay, we'll continue tomorrow whenever we have the next class. Okay, please go through this. I'll send you these notes also. Once we finish the shortcut, you can go through all of these things. Okay. Thank you so much, people.
Sir.
We'll meet again. Thank you.
Thank you, sir.
Thank you, sir.